Today under statistical thermodynamics we will be looking at the rotational partition function, and this rotational partition function is specifically for diatomic molecule. Now for diatomic molecules, like we have say HCl, or we have say hydrogen, we have oxygen, we have HF and other diatomic molecules. So these are homonuclear molecule, while HCF and HF are the heteronuclear molecule. So on the rotational partition function, we could write it as QR is equal to summation GR e raised to minus ER upon KT, where ER is the rotational energy and GR is the rotational statistical weight factor. Now the rotational statistical weight factor for the rotational partition function, it is obtained by 2j plus 1, where j is the rotational quantum number. J is the rotational quantum number. Also the energy is obtained from the quantum mechanics, that is from the solution of Schrodinger equation for rotation of the rigid rotor, and basically we are considering the rotation around the molecular axis. So the energy of rotation is given by J into J plus 1 h square upon 8 pi square I, where h, as we all know, it is Planck's constant, I is the moment of inertia, and it is obtained by mu r square, where r is the distance between the two atoms that are held together, and mu is their reduced mass. So mu is the reduced mass, and it is given as m1 m2 upon m1 plus m2. So when we substitute the statistical weight factor and the energy in this expression, and then we integrate this expression, the solution we get is 8 pi square I kt upon sigma h square, where all the terms are known. K is the Boltzmann constant, T is the absolute temperature, H is the Planck's constant, and sigma, it is known as the symmetry number, where this symmetry number, it is equal to 1 for heteronuclear atoms like we have say HF and HCl, and sigma is equal to 2 for homonuclear atoms like H2, O2 and other like N2 and other homonuclear atoms. So because in homonuclear atoms, when we rotate any particular molecule by 120 degree, the same configuration will arise, and as a result we need to divide the whole expression by 2 in order to obtain rotational partition function. Now further, these terms, that is h square upon 8 pi square I k, this could be written as theta rotational, and this theta rotational has the unit of temperature, and hence it is known as the characteristic rotational temperature. So when we substitute this 8 pi square I k could be taken to the denominator over here, and hence we will have q rotational is equal to T upon sigma theta rotational. So this is also one of the form of the rotational partition function. Now further, QR, it also rotational partition function could also be written as kt upon sigma hc into b, where c is the velocity of light and b is written as h upon 8 pi square I into c, and this b is known as the rotational constant. So when we substitute the value of b over here, we will get the same expression. So all these three expressions, that is 1, 2 and the third expression, this third expression is used for diatomic molecules only. Now for polyatomic molecules, similar expressions could be obtained, and for molecules having 3 perpendicular rotational axes like we have ammonia PCl3 or CH3Cl, the expression is given as QR is equal to 8 pi square 8 pi cube ABC raised to 1 by 2 kt raised to 3 by 2 upon sigma h cube, where A, B and C are the moment of inertias along the 3 perpendicular axes, and other terms are known. So for molecules like ammonia PCl3 and CH3Cl, this expression could be used. So hopefully the expressions are clear. Thank you very much.